We are back again for our third week's journey. We are going to talk about the integral today. There are two things which you always think about when you think about calculus. One is integration and one is differentiation. Now, what I want to emphasize is the following, is that one of the key things what integration does for functions of one variable is to find an area under a curve. Of course, you can ask me what is the definition of area blah under a curve and blah blah things. So, we presuppose that you have an understanding. So, essentially if you look at the screen, these are the two aspects of integration that is usually done in a very basic high school course when you are doing your 12th standard. That it talks about the antiderivative, which is the first thing that you talk about. That is, if I am given a function, find another function. So, given a function f, find a function capital F such that f dash of x must equal f. So, this process is called the process of taking the antiderivative. Now, let me look into something very carefully. That is, this process is slightly not so trivial. One might think that I can give me any function, I will find its antiderivative. It is not so easy. For example, if you take functions like e to the power minus x square, then I really do not know if you can find an antiderivative. You really can't find an antiderivative. But you should also simultaneously understand the following, that if I can find the antiderivative, the integral does a fundamental job. It finds the area under the curve. So, for example, here I am trying to find the area under the curve y equal to x cube from 1 to 2, and this calculation is absolutely known to you, and I just do not want to repeat it. Now, I want to show that how beautifully this idea of finding an area under the curve can lead us to one of the most fundamental results in calculus called the fundamental theorem of calculus. So, how do I look at an area under a curve? Suppose I have a curve which is given by y equal to function of t. I will tell you why I am taking t now, you will soon see. T is just a dummy variable, you can take z also. Now, suppose I do not know, I want to take the curve defined say from 2 to say 5. I want to find the area of this curve, and this curve has a property that f of t for the moment is strictly positive, non-negative does not matter. We will soon see, just keeping ourselves to non-negative functions and explaining the things will do the job, because if the function becomes negative we will tell you exactly what to do. Now, how do you talk about an area? Of course, you understand what I mean by an area. If I by area under 2 to 5 means I am really looking into this. But here we are in the domain of analysis of calculus, and hence the first question is, can we think of area as a function? We will talk about indefinite integrals also. For some people thinking, okay, why are you coming to definite integrals, why not indefinite integrals, but we will talk about them. But let us first look at this picture, that how do I start finding the area. So, how do I first start to find the area? So, I will define what is called an area function. So, let us again look into this function f, which I have drawn t and f t, t and y, and okay, this is nice, and this is 5. What I do, I will take some point x lying between 2 and 5. Okay, let me just consider a point x which is lying between 2 and 5. Of course, you can consider 5 or 2. So, let me just consider any point. For the moment, consider an x which is neither 2 or nor 5, and then let us look at the area from 2 to x. is this. Now, if I slightly change my x, I keep bring it here say x dash, then I have a different area. So, you have added some bit more of mass to this new area. So, what happens that, so if at x dash and x, let A is the area function which gives you the value of the area from 2 to x. So, A x dash is this. Of course, you can see that A of x dash is strictly bigger than A x. So, now if I am trying to find an area by using my function data, the interesting question is, and by integrating the function f, the interesting question is, if I can think out such a function A x, does A x have a derivative? Is A x a continuous function? Of course, by looking at the picture you can immediately make a immediate guess that A of x would be a continuous function, because if I move from 2 to 5 in a continuous fashion, my area also changes in a continuous fashion. If I move a very little bit from x, if I make x plus delta, the area also changes by that little amount. So, it is question is pertinent that can I find the derivative of the area function, and what is that derivative? If the derivative is f, then I can, so A is the antiderivative of f, and so by integrating f we can actually find the area. Okay. So, what I mean by the derivative of the area function? Okay, you can ask me more questions whether it exists, etc., etc. Let me see how to handle it. So, this is the definition. Now, once I have done through, let me look at the picture. So, I want to know what is the area Ax plus h minus x. So, I have this function, I am just doing it with 2 to 5, but you need not bother much, you can say any alpha to beta. So, let me come here x, and then I could go back or go forward, does not matter, just I am taking x plus h, just taking h positive for this moment, you could take negative. So, first you took look at the area, whole area over up to x plus h, 2 to x plus h, which is Ax is this, to this is A of x plus h. So, this block, this is denoting A of x plus h, and now this block is denoting A of x. So, what does that do? So, this area, this block of small chip of rectangular thing, this block, okay, it does not look like exactly a rectangle, there is some curve, but okay, because if h is very small we can consider it to be a rectangle just by using our Taylor expansion idea that when h is very small, then it almost becomes a tangent. So, we can approximate it to be a rectangle. Approximation is also one of the sole or the key ideas in mathematics. Now, so this shaded area, this black area is this is your A of x plus h minus A of x. So, this thing is your A of x plus h minus Ax. But how do you compute that rectangle? That is the question. Okay, I assume that there is hardly much difference between x plus h or x minus x or x plus h. So, let me take the area is nothing but the base h, the breadth, and the height I just take it to be fx. The difference between f of x plus h and f of x is very less. So, this area which is this A of x plus h minus Ax is nothing but h into f of x, because I am telling the difference is so less that I need not bother. So, A dash x is now limit h tends to 0 h of f x by h, and that is not limit f x h tends to 0. Of course, there is no h here, no h dependence, so it is f x. You can say that, oh, I am not happy with what you are telling. Why did you take your f x to be the length of the game, length of this rectangular type of thing that you are talking about? I can take a to be this to be x plus h. I said okay, does not matter. So, it will be now h into x plus h. So, if you want to take that length, so you want to take, so I took the left hand side as the length, you can take the right hand y coordinate as the length. So, then also we have, so now this will be the length f of x. So, this was your f x. So, this was your f of x and this was your f of x plus h, this length. So, I have now limit h tends to 0 f of x plus h, but if f is a continuous function, you can always, when you have a continuous function, you can always pull in the limit inside. This is one of the key features about a continuous function which I have spoken about when we spoke about continuous function, and when you put h 0 here, so that the x plus h, the limit of x plus h when h tends to 0 is 0, you have this is nothing but f of x. So, whatever you do, you show that once you want to compute the integral from 2 to x, then your antiderivative is f x. So, Leibniz gave this formal symbolism to it of the area function. So, I can take it from any a. So, it can be 2. So, 2 could be a and b could be 5 could be b. So, a to x f t dt, that is called the area function, and that is due to Leibniz. Of course, do not take me into issues about what actually an area is and what are those are issues which okay we have some understanding about, we do not want to get into all that. Now, you can ask me one important question. Now, you okay a dash x is the antiderivative of f x. So, what is the form of what is the form of a x? So, a x, so what is the form of a x? In general, a x would be of the form because a dash x would anyway give f x. But you say okay, you have a constant added here. So, which one do you want to mean that for same x you have different values of the area? I said no, it cannot have a different value of the area, this c has to have some meaning. Of course, you know if I come to this end point, say t equal to, I will put x equal to a. What is the area value of a? The area at a is 0 because the length, the breadth is 0. So, area is 0, a of a is 0. So, if a of a is 0, it would imply that I put a here and a here. So, a of a is equal to f of a plus c. Now, a of a is equal to 0. So, 0 is equal to f of a plus c. So, I just put x equal to a here, putting x equal to a. So, which you can understand, here I have put x equal to a is 0. So, what is c? C is equal to minus f a. So, that what does it mean? It simply says that a of x is equal to f of x minus f a, and this is what essentially is the fundamental theorem of calculus. When you write it down, it simply says, if you take the notation of, so if you have a continuous function which is non-negative in the intervals a to b, then if I take any point x which is strictly bigger than a and strictly lesser than or equal to b, then I will have and of course, you can write a to b f t dt is equal to Fb minus Fa, and what we have reached is, though you can ask there might be some issues about rigor, but what we have reached is called the fundamental theorem of calculus. You see how beautifully and how simply we have arrived at that conclusion. Now, what about if I take negative function which also takes negative value, like y equal to sin x? Is minus pi, right? Pi. So, what about this area and how to calculate this area? How to calculate such areas? This is one example I am giving. Or you can take a more general setup. So, now you know when the function values are becoming negative, note the area function Ax, when you want to compute the rectangular length, if you have this A of x plus h minus Ax here, because the function values are negative, the area of the rectangle would have a negative sign. So, basically you calculate the area of this curve, the area under this part, and you calculate the area under the non-negative part, and you subtract them. So, you find take the area A1 and make this area A2. So, basically when you add, they will look like subtracting, because here the function values are negative. So, when you, this is your particular breadth, say 1 centimeter or h or whatever, and then what do you have? You have this length, which is the function value, which is negative in this case. So, the area would give a negative sign, the area would come with a negative sign. So, when you add them, so it will look like as if you are to subtracting two areas. So, it will be basically A1 minus mod of A2. So, that would be the area when you have function. So, you can try out at home what the answer would be. It's interesting. Are you going to really calculate? People say okay. So, now once you know this, you know that the fundamental theorem of calculus can be proved even for non-negative functions which are not completely non-negative, have both positive and negative parts. So, fundamental theorem of calculus now holds for all continuous now. Are you going to work this out and say okay, the derivative of sin x is minus cos x, and then you put pi and minus pi? The answer is no. The area here is symmetric, they have the same magnitude. So, here the answer obviously is 0. So, once you have these ideas, calculating integrals become much more efficient. Okay. Now, with this idea about the fundamental theorem of calculus, we would like to end our conversation, but we would also state this very important fact: if f dash x is equal to g dash x, that is f and g are two differential functions. If their derivatives are same, then they only differ by a constant, then f x must be say equal to g x plus c. So, if their derivatives are equal at every point, then the only thing they differ by is a constant. This is something which you have to remember. So, with this we will finish today's discussion, and then tomorrow we are going to talk about some interesting ways of calculating indefinite integral. We are going to talk and also look at definite integrals, and we will talk about how to we will give a list of some interesting integrals and all those things. That we will do tomorrow. You will see that that's just quite fun. So, you see how simply we have come to one of the most important results of calculus. You can ask me whether there was a rigor etc., with the calculation of A of x plus h. It was not that bad as rigor goes, but it is all right, but truly one needed what is called the mean value theorem for integrals, which I am not going to give you in the course. I would like you to figure out what is called the mean value theorem or MVT for integrals of continuous functions, MVT of integrals. Look at the web, and then using that, can you really give a rigorous proof to the fundamental theorem of calculus? We gave a proof which is not bad, not very non-rigorous, gives you a fairly good geometric and intuitive idea and brings you right up to the result. Thank you very much. Thank you for your patience.